Well, it looks like it's time. Welcome back, everyone. Kind of a small class today, but we'll still get through it. Any questions at all to start us out, folks? Okay, well, I hope you all had a great Halloween. We definitely canceled class, and that was kind of weird for me. I forgot to even pass quizzes back. That's not what we typically do on Wednesday. But I hope it was a relaxing evening for folks. And now with what we're doing today, let's see, the announcements are now over here. We're going right back to section 10.1. This one's a really short section, so we're probably going to finish this one before getting too far into class today. And then we're going to be working primarily in section 10.2. That one we might come back to on Thursday's class. And for our new up-and-coming quiz, number 11, quiz number 11 is going to be about setting up hypotheses and talking about the potential errors in section 10.2. So it's there early just so it can be there. I get kind of busy on Thursdays, but it's going to involve both 10.1 and 10.2. So we're not quite there if you started it early to run through the whole quiz. Although it never hurts to try. I mean, sometimes that's kind of fun to see what we know, what we don't know with what's coming up. So that's our announcements at the moment. Any questions or comments, folks, before we get started? Okay, well, we just finished off dealing with confidence intervals. And so now we're in a new land of statistical inference. For hypothesis testing, we need to set up a null hypothesis. This is a claim to be tested, usually the status quo, a statement of no change about the population, versus an alternative hypothesis. And this is what we're looking for as the researcher. We're trying to find evidence that the alternative is true. Then, after talking about a null and alternative hypothesis, the thing I'll come back to quite a lot is this right here. We made a big deal out of it on Monday's class. Let's do it again right here. There is only two conclusions you can ever give in hypothesis testing, and it feels restrictive. It feels unnatural. That's why this is a really tough concept. So let's highlight this in yellow just to give it its fair share of importance, and a couple stars can't hurt. And here's the conclusions that we can give. We're either going to reject H naught, or we will fail to do so. We'll never make a statement that the study found evidence that the null hypothesis H naught is true. That's not the kind of a conclusion hypothesis testing could ever give for us. So if we reject H naught, that means there's convincing evidence against that alternative, and we have information that, against the null hypothesis, and we have information that it's probably the alternative that's true. If we fail to reject the null hypothesis, we'll simply say, well, we didn't find enough evidence against the null, and in other words, there's not enough support for the alternative hypothesis in that conclusion. So other difficulty we discussed is there's three kinds of alternative hypotheses. And when we go to write down our set of hypotheses, the null and alternative, usually we think about the alternative first, because the wording of the problem is going to tell you we're trying to see if this is true, or we're trying to show that this new average has gone up, or something along those lines. They're always talking about the alternative in that context. So they're giving us that information. We'll set that up first. But the next difficulty after that is there's three types of tests. They'll either be right-tailed, look at the yellow there, versus left-tailed. And if we can't decide, we'll always go to the default test, the two-tailed test. The null hypothesis in this class will always be written with an equality. Some classes differ with that a little bit, but it usually doesn't cause too much trouble. We'll focus on what our book does and always use equality right here on the null hypothesis. So that's a lot of talking through these. We still haven't set up a single null and alternative hypothesis, but that's what we're going to start to do on example one. And these are really fast problems in the homework as well. All we're trying to do is set up an alternative versus a null hypothesis. And here's our very first scenario. Any questions before we give this a try, folks? Okay, reading through this is a really small set of context. It says, seat belt compliance in Massachusetts was 65% in 2008. Then it goes on to say, the state wants to know if it has changed. So for each of these problems, we'll define the population characteristic, write the null, then the alternative hypothesis in terms of that population characteristic. And so really every one of these problems kind of starts off like this. Let's do a three-step process. Step one, we want to define the unknown parameter or population characteristic, P. Already, this is kind of tricky. I said P, but you might have said, It doesn't necessarily have to be P. That's something we need to determine. There's two choices for our population characteristic. We'll either use P or we're going to use mu. And the only reason we decide to use P here is it looks like the data is categorical. That's what told me probably categorical data. 65% in compliance means 65% of successes in this case, and 45%, or excuse me, 35% of failures in that case. If they gave us something else like an average of 2.67 seconds, we would have used this instead. That would have been numerical data. But here we're going to go for P only because of this statement. So that's our population characteristic. And because it's a proportion, we can say proportion of all drivers in Massachusetts that are seatbelt compliant I'm going to just put a dot here. I'll fill in this set of ellipses in just a moment, because this is a good time to pause with hypothesis testing. It's really very tricky. There's not a lot of information given right here. And if this is all I said about P, we could lose this problem. Well, a point on this problem, you'd still get partial credit for sure. And what beside we could lose the whole problem. They're a bit of a jerk about this kind of stuff. Anyone see what's missing from our description P right here? To give a little bit more context or more hint about it, the trouble with a population characteristic like P is that it changes. Populations change with time. They're giving us data from 2008, and that's how the population was in 2008. The best estimate of the population characteristic was P at 65%. But already in 2009, it's a different population. The drivers change. That value P does change. So down here, it said the state wants to know if it has changed. So we're talking about the proportion of compliance in the current year or currently. I'll just say here, the proportion of seatbelt drivers that are compliant in 2023. Just to mention, we're dealing with the current information or the present. If they weren't necessarily talking about 2023, we could just say in the current year they're interested in. So to me, that's really kind of nasty in a way. We're talking about two population characteristics really all at once. We're talking about the current value of people who are seatbelt compliant, and we're comparing it against the 65% figure, which is the historical data. When you've decided that's historical data, that becomes the value that you're going to test. And I'll often write this down on the notes. Let me change that P to P naught equals 0.65. This has become the hypothesized value. And we see that in the alternative hypothesis and the null hypothesis. That hypothesized value is everywhere in these kinds of problems. Let's write here, 0.65 is the hypothesized value. We want to know in the current year if it's still 65% or if it has changed, is what they're asking here in the problem. So that's our step one. We write down the population characteristic. I'll always mention that it's a very tricky step. It's good to take some time with that. Think about the problem and the context, maybe read it a couple times. But after we're through that step, here's our step two. We want to state the null hypothesis. Well, actually, let me return to that assessment. Let's call this a step two where we do the alternative right here and the null right here. I said a two-step process, but null and alternative hypotheses are usually written side by side. So I'll think of it kind of in this way. Step two, write down both the null and the alternative hypothesis, but we're going to focus on the alternative first. The statement here is going to be, notice it says population characteristic right here. And we just indicate a population characteristic. That was P. It goes right into that location. and same from the alternative, whichever one we decide it is, and the null hypothesis. Whatever P is, it'll go exactly in that spot. So we can go back to the null, plug it in right there. Any questions so far, folks, on writing down the null and alternative? Okay, so again, we're focusing on the alternative hypothesis. That one's kind of hard to get to. And we have to make a decision. Up above, we have three different values we could pick. After you write down P, it's either going to be a greater than, a less than, or a not equals. And we have to use something from the context to decide which is which. If we can't decide on a greater than or less than from the context, we go to the default test and use not equals. Let's pause here for a moment. The directionality comes from this sentence somewhere. Anyone spot the key word that's going to decide one of these three symbols? Definitely kind of tricky, right? Again, this is the worst part about hypothesis testing. It's tough already to write down a parameter. That's a hard problem. And then even beyond that, we know our parameter is just going to go here and here, but there's like a 1 in 3 chance of getting the right directionality. But the one word that's going to pick it for us turns out to be that word right there, changed. They could have said the state wants to know if it has gone up. We would have used the greater than sign. If the problem said the state wants to know if it's gone down, we would have used the less than sign. But all they say is, has it changed? That means they don't know. It means it could have gone up and they want to find out if it does, and it could have gone down and they want to know in that case as well. They don't necessarily know a direction with what could happen in the present data. And so that one wording there gives us this symbol, a not equals, right there. Let me undo that in yellow. So I think this is probably the better highlighting in yellow to emphasize when it says has changed. We put it right there. Any questions about that so far, folks? Okay, next, I definitely need a different color. Let's go with green. We have the left-hand side. We know what P is. On the null hypothesis, we're just going to put an equality. We might as well put that in right now. We decided on the default test, not equals, because of the word changed. But the last thing we need is this. On the right-hand side of all of your alternative hypotheses will be the hypothesized value, and same for the null hypothesis. And we found it right here. That's the hypothesized value. Let me see if I can just force that into green. Let's pretend we used green all along there. Oh, that looks kind of bad. Let's fix it real quick. So the value 65% is often indicated as P naught, P sub 0, and this is the hypothesized value. So it plugs in down here in the null hypothesis, 0.65, and it goes over here in the alternative, 0.65 as well. Lots of different moving parts, but after you practice doing this 4 or 5 times, it does become a lot more easy to put it all together. Always the parameter is a little bit tough, I'd say, the population characteristic. But let's take a look at this again. We said the null hypothesis is the claim to be tested. It's the statement of no change. It's the statement of the status quo is maintained. So if the null hypothesis is true, we're saying the proportion of all drivers in Massachusetts who are seatbelt compliant in 2023 is the same. It hasn't changed. So that would be probably great. Unless their goal is to get like in the 90%, that would be better, right? 65% seatbelt compliance isn't terrific when you think about it. But if you find enough evidence, our evidence are going to be probabilities, we'll support this claim. With enough evidence, we'll say that the study found significant statistical evidence that proportion of all drivers in Massachusetts in 2023, seatbelt compliant, has changed. In other words, it's not the 65% any longer. Then they'll do a follow-up analysis. They'll probably give a confidence interval. If it's not 65%, then what is it? They'll estimate it with a range. So that's kind of what these hypotheses tests are going at so far. It's tough to set them up. So I think our author really is going the right direction with the way she presents her material. Talking about set hypotheses first in 10.1. The next section, we'll talk about the errors. We'll start adding just a little bit more information. Until 10.5, we'll put it all together. Looking for this eraser tool. Well, any questions at all, folks, on setting these two hypotheses up? Okay, we definitely need to try it again. So let's go over to part B then. I'll carry this down in the notes, just this part right here, just so we can refer to it as we go. And here's another one of those pretty fast problems. It says in part B, last year, a survey found that 45% of the employees were willing to pay for on-site daycare. The company wants to know if that has increased this year. So this one feels kind of similar in a certain sense, right? They gave us a percentage. The moment you find that percentage, I would write down this symbol. P0 equals 0.45, written in as a decimal. And let's just emphasize, you don't have to say this, but for the notes, I'll put, this is the hypothesized value. So now that we have that down, let's see what else we have. The survey found 45% of the employees were willing to pay for on-site daycare. Company wants to know if that's changed. They really don't give us a lot of information for these, but we're only setting up hypotheses, so that's about right. But if we were given a percentage indicating categorical data, and you wrote something like a P0, next thing we should write down is P. We have the hypothesized value for the right-hand sides, but now we need to say what exactly the population characteristic is itself. It's just like with confidence intervals. If we can't do this step, then we are doomed when we go to give a practical interpretation with the confidence interval, and the same with the hypothesis test. I would have no idea what to say. So let's start by writing P equals the population proportion. And I should mention, saying population proportion, that's just a style of writing this out. When we were in the confidence interval section, I think we said true proportion a lot. That's just a different way to say it, and it's equally correct. You're just emphasizing different things when you're using those kinds of words. I'll put here just as an optional thing to say. You could have said, or true proportion. So P is the population proportion of all of something. Anyone see how this sentence would be completed? Any volunteers for the last portion here? Yeah, go ahead. Exactly. Thank you for supplying that. It's going to be the population of all employees willing to pay for on-site daycare. It's probably super expensive, but that's pretty much our parameter. But just like in the last problem, we should probably add just a little bit more to be specific, because they said last year it was 45%. So we ought to say this year. Does that make sense? So I'll say in the current year or presently, or I'll just say this year. This year. Again, that's a challenge when you're doing hypothesis testing. A lot of these tests, not all of them, but for a lot of them, you're comparing historical data with present data. There's really two populations. The historical one, that would have been the population last year for this company, and the present population is what this P is really referring to. When we have that down, next thing we could do is, I'll put down in black the things that you would have pretty much guaranteed on every problem. When you state the null hypothesis, it'll go like this, H0. There's no equality here. We're just saying H0 is the statement, something happens, so we put a colon here instead. P goes in this location. Then we write HA, A for alternative, another colon. A P goes here. And now, right inside here, This is where I would focus on in the next portion of the question. It's much easier to fill in this right here and get a value out because it comes right out of context. But I also have to remind myself that you're pretty much just going to go equals right here. And so there's a little bit more you can fill in guaranteed. But I want to fill in this symbol before I get too much further. Anyone spot what the direction should be on this one? Is it less than, or excuse me, greater than, I should say it in the order I'm pointing at them, less than or not equals? I agree, yes. The key word would be that right there. If they said increased, we're testing if P has increased by putting in the greater than symbol. Good eye on that one. We have to use greater than for this hypothesis. Does that make sense to everyone? The equal versus the greater than here? Okay, good news about hypothesis testing is the alternative is the nasty one because there could be three options for what goes here, but you always put equals in this location, no matter what. Then we go to the hypothesized value and it plugs in both of these hypotheses. 0.45 here. Now, this is a statement that the people willing to pay for on-site daycare in proportion is still 0.45. Here it's saying it's gone up, 0.45. You could imagine why the company would want to test this here. They're looking to see if they can find evidence that they can get more money for doing their on-site daycare side business. So if this comes out as true, they'll get excited and start ramping up their facilities for that. If it tests as false, then they will be less excited and that project might just fall out. So sometimes the decision you make on these are massive. That's why the next section is about the kind of mistakes you can make in hypothesis testing. But this is where this problem ends. Any questions at all, folks, on getting through this one? Okay, to me, these problems are really great for practicing these kinds of scenarios because they're fast, they're direct. We're focusing on just how to assemble the hypotheses and not the extra noise in a real problem. So this is a pretty similar homework types question. But eventually the questions look like this one. So let's try it again with one more hypothesis. I can get that to work. There we go. Sorry for all the struggles with Microsoft Word. It's sometimes just not very friendly. Okay, so here's our new situation. And this is more of what we think as a typical statistical problem. We have a wall of text, one big word problem. We have to read it, dissect it, get the information out. So let's start right here at the top. It says, the National Center for Education Statistics monitors many aspects of elementary and secondary education nationwide, and their 1996 numbers are often used as a baseline to assess changes. So 1996 must have been a pretty good year for the Department of Education for some reason or another. Down right here, it says, in 1996, 34% of students had not been absent from school even once during the previous month. That's nice. In a year 2000 survey, responses from 8,302 students showed that this figure has slipped to 33%. Now already, they're throwing a lot of numbers at us, and that's a big challenge with statistics. Understand which numbers we need, which ones might be fluff. So let's pause right here and take a look at that 34%. That was historical data, and so that looks like a hypothesized value already. I would probably, the moment you find that, put here, P naught equals 0.34. Then they go on to say, they did a survey in the year 2000, and they had responses from 8,302 students. Well, that would be a sample size, although we may not need it here on these notes. When we do a full problem, we actually will come back to this question. We will need that information, so it's just good habit to write this down. Sample size N is 8,302 students. Now it says the responses from the sample of size 8,302 showed that this figure has slipped to 33%. We have to pause right here on that number. Would you all say that's a statistic, or is that a population characteristic? Or neither, potentially? Good call. It's based off a study with a sample size from the population. This wasn't the entire population. It was because this is a national program, there'd be millions of students. So right here, this value is a statistic. Let's write p hat equals 0.33. Now, that's really, really dangerous because if you look at our hypotheses here, we're going to define the population characteristic. That's not the danger. It's the hypothesized value. Now, this is suddenly extremely tricky because we have to know they're referring to the 0.34 when they say hypothesized value. They're never, ever referring to the statistic. So that's kind of tricky when we put all this together. Now it says, coming down next, officials would, of course, be concerned if students' attendance were declining. Do these figures give significant statistical evidence of a decline in student attendance? That's a good sentence to pause on. They gave us a directionality just right here. From the word decline, is that a less than, greater than, or not equals? Exactly. Decline means something is going down. So right from that one word here, we're going to be using that, the less than symbol, when we go to write our hypotheses. So what's kind of crazy is we're just still reading through this problem and pointing out things that we're noticing. Down below, okay, I guess the problem is over. These are the instructions. Clearly define the population characteristic using the context. State null and alternative hypotheses in terms of that characteristic. So we're back to exactly what we were doing before in the prior problems. This is just a more filled out kind of problem, I guess you could say. We'll start by writing down P. I'm using the color blue because it goes right here. And also it kind of matches with the statistic. P is not equal to 0.33, but 0.33 is an estimate of the unknown population characteristic P. So I guess blue does work for both of them. And we'll say P equals, I'm already forgetting the context. It says 34% of students had not been absent for school even once during the previous month. I think they mean the prior 30 days when they say the previous month. So no month is special. They're just saying what's happening last 30 days every day as they look at the data. So I'll write here, proportion of all students. When we say all students here, we could be even more specific if we wanted to. This is national data. So we can say all students in USA that have not been absent. They said even once. I'll just say have not been absent. We don't need to say even once to give that emphasis. We'll still have the right statement. In the last, I'll mention their work in the last month. Although it's tempting to say previous 30 days, I'm not completely sure how they're recording this information. So that'll be how I write down that population characteristic P here. Does that look right to everyone? Any additions or changes you'd want to make to that? Okay, once we have P down, let's go to step 2. And these are the hypotheses. It's H naught. We'll write P, then equals, come over here, HA, P, and because we're testing for a decline, we're trying to see if P has gone down, so we'll use a less than symbol. And again, only because of the word decline. Now, one question folks might have had is, why not test not equals? That includes a decline and also includes evidence of an increase as well. One reason for that is if the people here in charge of the data from this National Center of Education Statistics thinks it probably has gone down, they have evidence the statistic is less than 34%, then their test is more powerful if they do the left tail test than if they do the two tail test with the not equals. So if they are expecting a direction, then this becomes the more powerful test to get a real conclusion out of. But if they have no idea what's going on, you go to the default test here. It's less powerful, but it catches any deviation, a decrease or an increase right here. So it's in that way that this is the default. But if we find context that directs us to a less than, we have to use it. That's the real test they would have been using. Then with all that out of the way, go back to the hypothesized value, 34%. It needs to be written as a decimal, 0.34. It'll go here and here. That finally finishes off the problem. I'll put a little border here to say the problem's over, but that was the notes and how we put it all together. Well, any questions at all, folks, on the conclusion here? Yeah.
So, on this one, for using 0.34 versus 0.33, it's just like the population characteristic versus like statistic.
Exactly. That was the population characteristic for 1996. And these hypotheses will never test a statistic. They're only testing the population characteristic. You know, I think that's a really good thing to add to the notes. Thanks for asking that question. Let's put here as a warning and just additional information that p hat never goes here or here. And I won't draw any more arrows. I think we get the picture at that point. It's always the hypothesized value in that location. Or hang on. Yeah, p hat never goes there, but I think I was really thinking of that location when I was drawing those arrows to match your question, but also doesn't go here either. So the statistic is part of how we're going to get a probability to associate with the test, but it's not part of the hypotheses in any way. That's one thing that's kind of weird about these problems. And again, that's the major reason of bringing in this problem. It's exceptionally tricky because of that one detail. They gave us a statistic, and when we do a full problem, they have to give us the statistic. So this is like the better problem we need to study as well. Other questions or comments so far, folks, about any of these? Okay, well, we did it, folks. This is setting up hypotheses. Now, after setting up the hypotheses, the next thing the researcher is going to do, especially people doing a very important problem like this in example 2, they want to know what is going to be the consequence of their conclusion. If they reject the null hypothesis, then they're supporting that, but it could have been a mistake. If they make a mistake, they need to know the severity of those consequences. And also, if they don't find enough evidence, they will fail to reject the null hypothesis. And that could possibly be a mistake as well. We need to know how dire that mistake would be and counterbalance them against each other. Then, and only then, can we decide for something called a significance level of the test that we attach onto the hypotheses. So we're looking at how bad our mistakes could be to fine-tune the hypotheses further, and that's all essentially section 10.2. Let's turn to that next section and see how it goes. Oh, they're asking further questions. Keep the last item you copied. If you do, it may take longer to. I don't know the right answer to these questions. I'll just say no. So next section is 10.2. And because it's so important, especially in this section, when we're talking about errors in hypothesis testing, let's take a look at another set of generic hypotheses and talk about the only 2 conclusions we can make just one more time. So it says, consider the following statement of hypotheses about a population proportion P. The null hypothesis says P is 0.32, so the proportion is 32% as a percentage. And this one would be a two-tailed test, so this is saying, alternatively, it's not 0.32. So there's 2 conclusions. I'll start with the one that we typically want. That's a weird thing to say, but these studies have a direction or a purpose. Like on the last study, they're trying to see if the number of students who have been absent had increased. They were looking for evidence of the alternative hypothesis. So let's say for our first one, this will be our first conclusion. We reject H naught. So after we make that conclusion, we'll have to write down this statement. Just trying to pick a color. Let's go with this one. We'll write a practical interpretation. So now we're thinking of the conclusions. And when we reject that null hypothesis, H naught, here's where we're focusing on. I'll temporarily circle this. Our practical interpretation will be right there. We'll have to know what P is in the context, and we'll write out what it is. The interpretation is pretty much going to go like this. We have found significant statistical evidence that P is not equal to 0.32. So that will be the interpretation, but keep in mind, we have to write in what P equals, just like in confidence intervals for practical interpretations. So this is the good scenario. That means the thing that study was interested in, they were able to find evidence for it. They found P is not equal to 0.32. But these studies, we're getting random data, anything can happen, and we might not have supported the alternative hypothesis, even if it was true. So if we lack this significant statistical evidence, here's what's going to happen. Down here, we'll say we failed to reject H naught. But what we'll never say is we found evidence H naught is true. That's the one thing a hypothesis test can actually do for us. If we say we failed to reject H naught, then our practical interpretation this time goes like this. Again, there's a huge temptation to try to talk about this statement, but we'll never say we found evidence that P equals 0.32. In fact, the very first step when we run through the procedure of the hypothesis test is you assume that's true from the beginning. Then you find out how compatible your actual data is with that assumption and give a probability to it, which we'll call a p-value. So the very first thing is you assume that's true, just like in a court of law. So instead, we still focus on that statement, and we'll say for our interpretation, we have not found significant statistical evidence that H naught, oh, sorry, I must have lost my train of thought. We have not found significant statistical evidence that, and I should have gone right up here, P is not equal to 0.32. So our interpretations almost look the same. We'll either say we found evidence that the alternative is true or say we did not find that evidence. The conclusions are always fixating very strongly on your alternative hypothesis because that's always the drive of the research. The research question itself is contained right there in HA. But let's add one more emphasis to this. For either interpretation, we also have to say what the population, let's say it this way, just feels more familiar, say what the unknown population characteristic represents using the context. So by population characteristic, we mean this here and this right here. So those are the only two kind of conclusions we can make. And we're at the stage where we could make those conclusions. If we just said we found evidence HA is true, and just the last example about the research data, you would have been able to say exactly what that would have represented. So this is the breakdown of the two possible conclusions, but now we have to look at the errors we could have made. If there's only two conclusions, there's two types of errors we could make, and that means there's a type 1 error and a type 2 error. So let's take a look at those next. Any questions at all first, folks, before we take a look at those? Okay, so first, we have a type 1 error. What happens in a type 1 error is, if we reject the null hypothesis, and it's true, that can happen, our data is a random sample, and your statistic you get changes from sample to sample, by pure bad luck alone, you could reject a null hypothesis, which is actually true, and you've made a type 1 error. A type 2 error is the error of failing to reject the null hypothesis when it was actually false. In a type 2 error, we found that, in a type 2 error, we failed to find evidence of something that's actually true. We should have supported the alternative hypothesis in this error. So those are the two mistakes. And type 1 error, type 2 error, these are tricky statements. This would be stuff I definitely would put on my notes for the exam, but I would probably put it in this format, this table right here. Let's make a quick note just in case I forget, that'd be terrible. This table is very important for exam notes. It's hard to memorize this information completely because of the directionalities here are really tricky. But if you have it down in your notes, the skill that we need is know how to interpret the information as we see it in a current problem. So that'll be the major skill that's tested. Well, let's give it a try right here, starting on this problem. It says a television manufacturer states that at least 90% of its television sets will not need service during the first 3 years of operations. A consumer group wants to investigate this statement, and a random sample of 100 purchasers is selected. And each person is asked if the TV set purchased needed repairs during the first 3 years. Now, when you're talking about errors in hypothesis testing, type 1, type 2 errors, there's usually two groups. And if you make a type 1 error, you've offended one group, and if you make a type 2 error, you've pissed off the other group. In this problem, there are two groups that we're thinking about. There is the television manufacturer. So there's one group of individuals. And there's also a consumer advocacy group. Think of something like, or what was that magazine called? Well, there's a consumer group there for a certain magazine. I am drawing a blank on that. But think of a consumer advocacy group as maybe there could be one for air conditioners. They look at all the air conditioners released on a market, and they just let everyone know what the reviews are, the good buys, the bad buys, things like that. So there's a consumer advocacy group also in this problem. I'll say that this is the other group. So now we can set up hypotheses in this problem and talk about making a type 1 error or a type 2 error, but we also have to think about who are we offending the most when we make either one of those errors. One group might be more powerful, the television manufacturing group. If that's like Samsung, they're a multi-billion-dollar company. And a consumer advocacy group could be a small magazine corporation. They could be maybe $1 million company. They wouldn't want to offend the manufacturers necessarily. And so they have to be very careful when they go through these kinds of hypothesis tests. It goes on to say, let P denote the proportion of all TV sets made by this manufacturer that will not need service in the first 3 years. Now that's really kind of nice. They just gave us the parameter P. That can happen on quiz problems and real exam problems, sometimes in these kind of situations. So the problem isn't so very, very long. Next, it says the consumer group does not want to claim false advertising unless there is strong evidence that P, the proportion of the TV sets that will need repairs within 3 years, is less than 90% or 0.90. So for that information, they're asking us, what is the null and alternative hypothesis that the consumer group should use? So we're thinking of being actually part of the consumer group. Imagine you're, say, the director or the editor-in-chief, something like that. And you're going to write down these hypotheses very, very carefully. And also think about the errors you might make. We'll look at those in the next following parts. So start off like this. I have different color coding on this page of notes. I'm going to keep blue as type 1 error, green as type 2 error, since that's the tricky thing we're trying to investigate. So I'll put P equals. And the problem right here said they're looking for strong evidence that P is less than 0.90. The concept here is the alternative hypothesis is what the researchers, now the consumer group, is most interested in. So we can pen in P less than 0.90. They pretty much told us that's what they're interested in. They told us specifically the alternative hypothesis. Then if there's a 0.90 here, there's a 0.90 here as well. That's one thing that always matches in hypothesis testing. The right-hand side here becomes the right-hand side here as well. So we've got it, folks. That's our null alternative hypothesis. And honestly, it's because it was fast because the problem kind of did a lot of it for us. They gave us the parameter and they told us what to test as well. But this problem is focusing on the errors we can make. Let's try type 1 error, see how far we get, and we'll call it a day after that. That sound like a okay stopping spot for folks? Okay, let's focus on type 1 error. It says, describe what a type 1 error represents using the context. Now, saying using the context is really very important here. You can put down on your paper, type 1 error means you rejected H naught when it's true, but that's not the practical interpretation we want. We want to describe the meaning of that. So I would probably put this down when I solve this problem. It's asking about a type 1 error, so I will put down we rejected H naught when it's true. But now below here, we're going to write our official answer, and this is really just the guide. So it's a practical interpretation of what we're going for. We have to bring in the context. So here's how we can write it out. Let's look again. It said we rejected H naught. That means we're supporting this if we reject H naught. Let's write out what that would say. We can't put P down. We have to write out what P is, but it's indicated right here. So the practical interpretation would go, the proportion of all TV sets, sensing the need for more white space, let me get that in there, made by this manufacturer that will not need service in the first 3 years in the first 3 years, then we could say is concluded to be less than 90%. Let's put this next portion in purple to let it pop out here. We made the conclusion the alternative is true, so we'll say is concluded to be less than 0.90, or you could say 90% if you prefer. But this isn't the whole thing. We need to say very next, given that. If you say given that, you're thinking conditional probability, and that's exactly what these are. It's rejecting H naught, given that H naught is true. Or you could say when in fact, because that's what a type 1 error is as well. We rejected H naught when in fact it was a true statement. So let's write it down that way. You could say given that, but I think when in fact is emphasizing what we really need to say a little bit better. So we concluded it's less than 90% when in fact it equals 0.90 or 90%. Let's think about this. Who would this upset the most? Would it be the consumer group or would it be the manufacturer group? Definitely. We just said that your TVs are terrible. Less than 90% are going to need repair, or excuse me. Yes, less than 90% will not need service in the first 3 years. That's a weird way they wrote down that parameter there. And so this offends, let's say upsets the manufacturers the most. So if we make this type 1 error as a consumer group, we could be in really, really hot water. You might get legal letters of cease and desist. All sorts of bad things can happen to your business. If it were a big giant like Samsung, Sony, they could just bury you and end your business. So this is probably an error they really want to avoid. But you have to compare that to type 2 error. We're balancing bad with bad when you think of the errors in hypothesis testing. And that's what we'll come back to next class when we look at the other kind of error we can make. Well, any last questions, folks, before we call it a night? Yeah, go ahead.
When these hypotheses, why is the focus on like rejecting instead of like affirming the hypothesis?
Affirming which one?
I guess my question is like in general, like why is the wording focusing on like rejecting versus like affirming?
It's mainly because whenever we go to write down any set of hypotheses, the logic really comes from this kind of information here. The null hypothesis is always a statement that we assume true right away. So we're rejecting that true statement or we're failing to reject that true statement in hypothesis testing. But we'll see once we go through the full process of the hypothesis test in 10.5, assuming the null is true, whether it's this silly example or this one, it's the first step in actually getting the probabilities we want to make a conclusion. So because we always assume this is true, we'll either say we've rejected it, that's our goal, or we fail to reject it. But does that help out with your question there?
Yeah, I think so. It's not really like anything that.
But it's more kind of like a general question, yeah. I think that's where the major motivation goes from, that specific language of reject versus fail to reject. The fact that we're fixating on essentially saying the null is true, running through the study and seeing how badly the data is even compatible with that statement. But other questions at the moment, folks? Okay, well, have a great night. When we come back, we'll finish off this example 2, and then we should get through example 3 as well. I might put out a new set of notes, but I think that might be a little bit early. So just in case there'll be extra notes, I think this is about where we're going to end on Thursday.